Hey, it's Dr. J. We're going to learn about rational functions today. So we've been talking a lot about functions and graphs and polynomials and all sorts of behaviors. And this is kind of the grand finale of that concept. So a rational function is defined as a function that is the ratio of two polynomials. So P and Q are polynomials. So most of these graphs are descended of the reciprocal function. That we learned previously. Remember, the reciprocal function was 1 over x. Yeah. So remember, when we drew the graph of the reciprocal function sort of looked like, let me just draw a little quick sketch of it up here. I'll do much more detailed graphs as we get into the lesson. But remember, the reciprocal function had these asymptotes. And initially, the asymptotes are the x and y axis, but as you recall, when we went through the transformations, when we shifted the graphs up and down and left and right, those asymptotes might move around the page. But just to get me started with this basic definition, the basic shape of the majority of the functions we're going to talk about today follow this same basic shape of the reciprocal function. So you have a horizontal asymptote and you have a vertical asymptote. Now, we've already discussed the sort of primitive versions of these in a previous section. So today we're going to get a little bit more into the details that are sort of leaning towards the calculus realm of mathematics. You could even consider this a pre-calculus intro lecture. So let's start off with some definitions of domain. We talked about domain. So the domain of a rational function is the set of all x such that q of x, that's the denominator, is not equal to 0. All right. Now, I'm using set notation in the definition. I'll probably present it both ways. I'll present it with set notation sort of initially, and then we'll expand it into the classical or the interval notation that we've classically been using throughout the course. So that's the domain. The vertical asymptote or asymptotes, we'll start off with just one asymptote, but eventually there might be more than one, are the x values are given by the equations x equals h1, h2, up to hn, where q of x is equal to 0. So for any of these x values on the x-axis, it creates a vertical asymptote. Now, I made this look a little bit more complicated than it actually is. For the initial values, there will just be one vertical asymptote. All right, and then as we expand into the lesson, we'll have multiple vertical asymptotes. So you can also say q of h is equal to 0. It's interesting that we call them vertical asymptotes, but we use the letter h. Yeah, that's because it's a horizontal shift. So if this asymptote gets shifted over, which it very well might, on the x-axis, it gets shifted horizontally, the asymptote is still vertical. All right. And we covered that before when we were talking about the transformations of functions. When you move something left to right, we use the letter h, but the asymptote, or the line, if you think of it as a line, is x equals h. And that's a vertical line passing through x equals h. All right. So that's the vertical asymptote. And it'll get more clear when I actually do an example, but just kind of write this down so you have some frame of reference. The next thing we want to talk about is the horizontal asymptote. Now again, initially, in the reciprocal function, the horizontal asymptote was rather simple. It just lied right on the x-axis, so it was the equation y equals 0. But in this lesson, the horizontal asymptote will be y equals k. I'm going to have to erase this for a second. So the horizontal asymptote and there is only one horizontal asymptote. With verticals, I always leave the possibility that there could be more than one. But with horizontal, it's much like a y-intercept. There's always only one horizontal asymptote. So this is where it gets weird, all right? Horizontal asymptote is determined by the end behavior. We talked about the end behavior as x approaches negative infinity. What happens to the function f of x, or the y value? It approaches a limit of k. So as x gets very large, I like to call this large negative, although technically it's small negative. And as x approaches positive infinity, what is happening to the value of y? The y value, also known as f of x, is approaching some value called k. Right? And so our graphs will sort of resemble the reciprocal function that we saw in previous lectures. All right, so this is the basic shape of the reciprocal function. All right, so those are the three things that I'll be asking about initially. I'll be asking for the domain. I'll be asking for the vertical asymptote. That's x equals h. And the horizontal asymptote is y equals k. So they're given by equations. All right, so enough of the introductory theory. Let's get right into some practical examples. And I'll ask you these three questions about this example. So we'll go ahead and call this example 1. So f of x is 8 over 3x minus 9. And just to sort of annotate and how this relates to the original definition, the numerator is called p of x, and the denominator is q of x. It stands for quotient. Although some people use d of x for the denominator or the divisor, I'm using p and q. I think that kind of matches up with previous terminology. Remember we talked about the p's and q's previously. So p is the numerator and q is the denominator. Now this is a pretty basic example. Look, p of x is a polynomial of degree 0. Right? It's a constant function. Right? So it's not a very big polynomial. And then the denominator is a polynomial of degree 1. So it's a linear function, or a linear polynomial, degree 1 polynomial. All right, so let's get right into it. The three things that I'm going to ask are to find the domain, the vertical asymptotes, and again, there may be more than one, but initially there's pretty much only one, until I tell you there's more than one. And then the horizontal asymptotes, or horizontal asymptote. There's only one horizontal asymptote. All right, so for the domain, we take the denominator and you set it to not equal 0. Yeah, the denominator cannot equal 0. You cannot divide by 0. So we have 3x minus 9 cannot equal 0. So 3x cannot equal 9. I mean, you guys have been watching my videos for a long time, so I'm going to start expecting a little higher level of math here. So I'm adding 9 to both sides. And if you want to write that, fine, I'll do it one more time here. Plus 9, maybe you've been a little rusty on this type of thing. You add 9 to both sides, you get 3x equals 9. Then we'll divide both sides by 3, and you could do most of this with mental math, unless the numbers come out a little bit strange, then you might want to double check. So it's x is not equal to 3. All right. So the domain, say DOM, is the set of all x such that x is not equal to 3. All right. Be careful. Don't just say the domain is x not equal to 3. That's not the domain. This is what's called the exclusion. There's one number that's been excluded, 3. All right. So the domain is all x's except 3. All right, so the domain is everything except for what x is not. X is not 3. There's another way to write this. I sometimes ask for set notation, but sometimes I'll ask for interval notation is more advanced or calculus-like notation. We say negative infinity, comma 3, open parenthesis. So it's not including 3. Union, open parenthesis, 3 to infinity. So this is the more common sort of calculus way of writing it. But you can still look at the definition. I always remember the definition as being the set of all x's. Okay, so that's the domain. Now, the cool thing about domain and vertical asymptotes is they are sort of the opposite of each other. The domain is everything except 3. And so the vertical asymptote, you just take this and remove the not equal to and say x is equal to 3. So whenever you have the domain, you automatically get the vertical asymptote as well. Okay, and there might be some exceptions as we move along. When you have multiple exclusions, it gets a little trickier. But since this is example 1, I'm just sort of showing you the basics. All right. Finally, we have the horizontal asymptote. All right. Now I'm going to need to use this space, so let's just erase this. I'm just going to write DOM is the, down here, negative infinity to 3, union 3 to infinity. And then I got my VA, vertical asymptote. Now that's an equation, x is equal to 3. And then my HA is, I don't know yet, I'm going to do the work for that next. All right, for the horizontal asymptote. So what we do is we let x get very, very large. Or you can let it get very, very small. Yeah. We're going to let x get very, very large or get very, very small. For the sake of brevity, let's just use this one. It turns out that whatever value you get when x gets very, very large towards positive infinity, you're going to get the same value when x gets very, very small towards negative infinity. If you don't believe me, well, I don't see why you wouldn't believe me, but I can easily demonstrate that if you plug in a very, very large number for x, the same thing is going to happen as if you plug in a very, very small number. Now, it's difficult to plug in infinity. So what we do is we use a very large number. Something like, I don't know, 1,000,000 or 1,000 or 100,000. Let's go with 1,000,000. Right? Although it turns out you can use 100 if you want. 10 is not quite big enough to demonstrate the property, so I'm using 1,000,000 to be extreme about it. So I'm going to plug in this number, and it's sort of simulating infinity, right? It's a simulated infinite value, right? although we all know a million's not really infinity. All right, you can use as large of a number as you see fit. So you plug it in for x. So there's a million. You get 8 over 3 times a million minus 9, which is 8 over 3 million minus 9, which is 8 over 2,999,991. You could do that on a calculator if you want, and you know what you're going to get? 0, 0, 0, 0, 0, 0, 0, 0, 0. It's going to fill up your entire calculator screens with zeros. Although there is probably a digit down here at the very end, but it's so small, the value has so many zeros. Maybe it doesn't. Let's see. I got an old-fashioned calculator here. Let's see if it actually shows up on there. I got 8 divided by 2,999,991. Oh, yeah, there's a 2 way down there. So 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6. And then there's a 2, 6, 6, 6. But I hope the point was made. I only used a million. If you use a billion or a trillion, or as you approach infinity, this number is approximately 0. Yeah. In fact, you don't actually have to plug in the number. I mean, I'm a math teacher, so I want to demonstrate the mathematics behind it. And I might do this a couple more times as we go through this lesson. But in general, you know, you can just think of a very large number in your mind and then look right here and ask yourself, what happens when this number is really large? And clearly you have 8 divided by some very, very large number. I'm always worried about whether I have the right number of numbers, so I like to use the commas. So that's 3 million, and that's 2,999,991. Well, needless to say, the value is very, very close to 0, and so we say the horizontal asymptote is y equals 0. Okay. We could draw a rough sketch of this graph. Perhaps in a minute I'll use the graph board or maybe even use the computer to show some virtual graphing. But for the time being, this question has been answered. Domain, vertical asymptote, horizontal asymptote. Sort of a quick graph. Not a very detailed one, but I'll just call this a quick graph. You draw your x and y axes. You draw your vertical asymptote, which is x equals 3. That's a terrible axis. Let me try that again. That's not much better, but all right. So that's your x equals 3. Then you have your y equals 0. That's your horizontal asymptote. Okay. And then you pick a point, perhaps, I don't know, 4, right? Just a point on the other side of the asymptote. If I plug that in here, right, I get f of 4. This is just to kind of get a quick graph here. I get 8 over 12 minus 9, which is 8/3. So right about here. Yeah, 8/3 is what? 2 2/3. So I'm not being very precise, but you know, right about there. You could also pick a point on the other side of the asymptote, something like 2. Right, try that. F of 2 would be 8 over 6 minus 9, which would be 8 over negative 3, which would be negative 2 2/3. So that would be somewhere down here. And As I mentioned in the introduction, it looks just like its descendant, the reciprocal function, or what we used to call the mother function. So there you go. That's a very quick graph. I just drew the asymptotes. I plotted a couple points to get an idea. If we want more detail, or if we need more detail as the problems get more sophisticated, we'll probably use a more sophisticated method. But that pretty much summarizes the concept. All right. So that is your first example. The next example (3x minus 2 over 2x minus 5). Oh, there it goes again. Let's see if we can bring it back to life. There we go. I've told you this before. I turn the autofocus off, but it seems to come back to life when we least expect it. All right, same question. Find the domain. Find the VA, the vertical asymptote, and the HA, the horizontal asymptote. All right, domain. We're going to set the denominator to not equal 0. And solve. And there you go. That's your domain. So again, in set notation, it would be the set of all x such that x is not equal to 5/2. You can also use a decimal. It'd be 2.5. I've mentioned this before about decimals. They're not really outlawed in this section or in any of my lectures, but whenever they give us, unreasonable values, repeated values, or irrational, decimals that just go on forever, like square roots of 2 and things like that, we typically try to avoid them whenever possible. But what I recommend, and I've recommended this before, write 5/2, but think 2.5. Yeah, because that's probably the way your brain thinks, right? 2.5 or 2.5. You can also write it this way: negative infinity to 5/2 union 5/2 to infinity. All right. This is probably the way that the assignment will be presented. So when you type it in, these are not so easy to type on a computer, but sometimes we have that interface that allows you to use the brackets. It'll have like a box right here that you fill it in. But just read carefully, and if you're not sure, shoot me an email. I'll let you know how to do it, which way to enter it. All right, remember you get the buy one, get one free, so you also get the VA. The VA is an equation. You just remove the not equal to, and you say x is equal to 5/2. So there's your vertical asymptote. Now for the HA, you're going to let x get very, very large. Yeah, infinity. Or if you choose, you can use negative infinity. You can let x get very, very small, right? Negative 1,000,000. We call that a very, very small number. Okay. To show you that you don't have to use 1,000,000, you can just use something like 100, or let's do 1,000. I never feel like 100 is a very big number anymore. In fact, maybe 1,000,000 isn't really a very big number anymore. But just for the sake of simplicity, let's use 1,000. So we're going to plug in 1,000. You could probably do this mentally, but that's going to be 3,000 minus 2. And that's going to be 2,000 minus 5. Yeah. So here's where we're going to estimate things, right? This is where it's very important to sort of estimate. This is approximately 3,000, right? the -2 doesn't really do much to the 3,000, right? Yeah, it becomes 2,998. But 2,998 is basically 3,000, yeah? Similarly here, this is 2,000 minus 5, which is 1,995, but that's still basically 2,000. Yeah? We're looking for a tendency or a limit at which it's getting closer and closer and closer to that number. So it's not exactly this number, but it's approximately this number. And then 3,000 divided by 2,000 is 3/2 or 1.5. Yeah. I actually would prefer 3/2. So our horizontal asymptote is y equals 3/2 or 1.5. All right. Now again, you could use a negative number, right? And then this would just be negative 3,000 divided by negative 2,000, right? They'd both be negative, and then you'd still get a positive 3/2. You could use a much larger number. Yeah? Because remember, you're trying to simulate infinity, right? What does it feel like? What does it behave like as it gets larger and larger and larger? So if you want to use a really, really, really large number, well, that's fine. This is just going to be 3, I don't even know how many zeros that is. And this is going to be 2, 0, 0, 0, 0, 0, 0, 0, right? Simulating infinity, and it's still going to come out to 3/2. Okay. So in that case, you could just use 10 or 100, all right? I don't. I always start with like 1,000 or something. But in fact, as you get better and better at it, you can just look at the original problem and go, oh, okay. As x gets very large, that thing gets very close to 3/2, right? Because there's a behavior going on here, right? We might formulate this into a case-by-case basis that will make this process a little bit easier. Okay. To draw the graph, again, I'm just going to do a quick graph. Sometimes, to graph, we sometimes use intercepts. I didn't do that in the last one, so I'll say we often look for intercepts. And the last one, I just skipped that part. I just used random points. But intercepts are something that we've often done in other sections where we plot the x and the y-intercepts on the graph. The y-intercept is by far the easiest. Yeah, you just plug in 0 for x. And you get -2 over -5, which is 2/5. So you'd say 0, 2/5. That would be your y-intercept. I probably should not have boxed that yet. Yep, 0 and 2/5. That looks like a 6. Let's make it look like a 5. 0 and 2/5. So that is by far the easiest point, the y-intercept. The x-intercepts, you want to set the numerator, which was called p, equal to 0. Just the numerator is p of x. Remember, the denominator is called q of x. Just for conversation. When I'm talking about these things individually, I like to call the numerator p and the denominator q. So I'm setting p of x equal to 0. And that's certainly not difficult, but I mean, you have to know your algebra. You get 3x equals 2, and then you divide. And this is the exact reason why I don't use decimals very often. For problems like this, if you did a decimal, this would be 0.66666, repeating sixes forever and ever. And that's not very easy to type in. Although some problems, I think in the past, we've done some problems where we used approximations, right? We'd say 0.67 or something, use some rounding rule. But nonetheless, this is now your x-intercept, which I'm going to keep it as a fraction, 2/3, 0. So that's your x-intercept. And this is your y-intercept. Once you have all this information, it's much easier to draw the graph now. And again, these are just quick graphs. I'm not really using a lot of detail here. Maybe I'll go kind of exaggerate my scale a little bit. So I've got my vertical asymptote is at 2.5. So 1, 2.5. Right, assuming each tick mark is 1 unit. My horizontal asymptote is 1.5. So 1.5 right there. My y-intercept is at 2.5, so that gives me this shape here. It's kind of a curve like this. I know that's not the best curve, but it's kind of like that. It's a curve that's curving up towards the asymptote like this. I know I say I'm doing a quick graph, and then I get all OCD about it and start drawing crazy stuff. And then my x-intercept is 2/3. 2/3. So 2/3 would be right about here, right? If this is 1, there's +1, there's 2, there's 3. 2/3 would be right about here. Something's got to be wrong here. So I got 2.5. I got 3/2. I've got 2/3. Oh, my y-intercept's in the wrong place. I was looking over here. Look at this. This is 5/2. This is 2/5. You see how drawing the quick graph kind of clears it up for you? There we go. So there's the y-intercept. So I was looking at the wrong one. See, I'm only human. 2/5 is right about there. And then 2/3 is right about here. Again, I'm not being super precise. That original curve I had here was not right. I was looking at the wrong number. These are asymptotes. These are intercepts. All right. And then just kind of copy the shape of the reciprocal. So remember, the reciprocal function has a curve in one area or one region, and then the opposite region. They're always in opposite regions. So that gives you your other side of the function. All right, sorry about that. I'm glad I caught it before I moved on. I might have had to start all over again, which I hate to have to do that. Okay. Example 3. So this one's written in a strange way, but I'm doing this intentionally to show you a different technique for graphing. We can find all the information. So find the domain. Find the vertical asymptote, the horizontal asymptote, and the intercepts. I regret not asking for range. I'm looking at my notes. I'm thinking, well, I didn't really ask for the range, but I mean, I guess I could, but I'm not going. I just didn't, I guess, for some reason. So find the domain, find the vertical asymptote, the horizontal asymptote, the intercepts. And this is a slightly different formulation. This function is what we call a transformation form. Yeah, transformation form, as the word form twice. It's a transformation of 1 over x. Yeah. And what's neat about this particular form is it tells you everything, right? It tells you everything. The negative is telling you it's been reflected. So it's been reflected about the x-axis. The 2 is a scalar. Yeah, so it's going to stretch by a factor of 2. So it's going to stretch it out by a factor of 2. Typically, it's a vertical stretch. Yeah. The 3, the negative 3, remember the transformation rules? That's going to shift it left. No, sorry, shift it right. It's opposite. Yeah. It's been so long since we did these. I almost forgot. X minus 3 actually shifts it to the right. Yeah. And then plus 4 is going to shift it up. So for this presentation, I can just go straight to the graph, right? A lot less solving going on in this presentation, because remember when you use transformations, it's as if the function has been transformed out of a seed and it already exists. It already is in its particular formation, and you can just simply write down all the answers. Yeah. So we take this mother function, right? Remember the mother function. Mother function kind of looks like this. Yeah. And we're going to reflect it about the x-axis. So it's going to flip over like this. So there's the mother function. Now let's go through the transformations. We'll kind of go through them all. So we're going to flip it over the x-axis. There's your x-axis. So it's going to flip over. So this guy comes down here, and this guy goes over here. Yeah. Then it's going to get stretched by a factor of 2. Yeah. So remember, vertically by a factor of 2 means that if this point right here was 1, then over here, so this point is 1, and this is negative 1. So here's negative 1. Yeah. Then over here, it's going to be 2 and negative 2. So with reciprocal functions, it's kind of hard to see the stretch. So I don't know. You remember vague, I don't know if it's a vague memory or a recent memory, but when we stretch a reciprocal function, it's kind of hard to see that it's been stretched because it still kind of looks the same. So really, the only indicator that it's been stretched is that value is now 2. Yeah. All right. And now we're going to shift it right 3 units. So now this asymptote that used to be right here is now over here. Okay. So this dot that used to be at negative 1 and 2 is now at 2 and 2. Okay, so that's 2 and that's 2. Right. And then this dot that used to be at 1, I know my asymptote should be on the line, but I drew it off to the side so you can see it. So this used to be 1 and negative 2 before the shift. Now it's going to be over here at 3 and negative 2. So down here like this. Okay. I know you might be thinking to yourself, well, shit, by now I could have just done all that algebra and solved all the equations, and that's fine. You could have done that. But I just wanted to point this out because when you notice that it's written in a different form, perhaps a slightly different technique might be in order. Or not. You could use the other technique as well. You might regret it. I don't know. I might regret having done this, but whatever. Now we get to but I'm still getting one more chance at teaching these transformations because this might be one of my last chances to do it with this class. So finally, each one kind of represents a different transformation. Now I'm going to shift it up. So up 4 units. So again, there used to be an asymptote here. And now this asymptote is going to get shifted up 4 units. 1, 2, 3, 4. Okay. And then I still have this one here. 1, 2, 3. I know I'm running out of room. Okay. And so now this curve is going to be over here. And then this curve is going to be over here. That's not the best graph, but that is the final graph of this function. Now, I did all of that work. You could probably, now that you've seen me do it step by step by step, you could probably just take this, look at the transformations, and jump right to this graph. I kind of wish I would have done that, but I wanted to just give one last presentation of the different transformations. All right, so the question was to find the domain, the horizontal, vertical asymptotes, and the intercepts. So let's go ahead and answer those questions. So domain, you can kind of see it in the graph. Remember, this is 3. This vertical asymptote is 3. So the domain is -infinity to 3, union 3 to infinity. That's your domain. The vertical asymptote, x equals 3. Yeah, it's the number that's been excluded from the domain. Horizontal asymptote, well, you can see it over here. It's 4. Yeah. Y equals 4. Now, the only thing this transformation does not give you is the intercepts. Right. I mean, unless you're using a piece of graph paper and you're being very, very precise about all these transformations, the transformations typically don't give you the intercepts very easily. So the intercepts, we just have to rely on the old method of plugging and chugging. So for the y-intercept, we plug in 0. Be careful with this negative out in front. This negative, I like to associate it with the 2. So it's -2 over -3. Again, I don't want repeating decimals, so I'm going to rewrite this as 2/3 plus 4 ones, 4 over 1. And I'm going to multiply by 3 to combine the denominators, and I'm going to get 14/3. Sorry, you can't see that. 14/3. Just barely down here on the bottom. So I'm going to write the answer up here. 0 and 14/3. There's your y-intercept. Sometimes you can reduce this fraction. Or sometimes it comes out to be a terminating decimal, in which case that would be okay. But this would, have a, it would go, 6666666, something like that. Forever. I guess it'd be 4.6666666666. All right, I don't really need the graph. The graph was just a kind of a showpiece. I'm going to show all these different techniques. For the x-intercept, I hope I can squeeze it in here. I'm going to set this equation equal to 0. Right? So essentially taking this equation and setting it equal to 0, like the y value is equal to 0. Right? Sometimes it's nice with these functions, I know I mentioned this before, to just rewrite it as y. And then you see that that's your y value right there. And so now you're going to solve this. You're going to move the 4 to the other side. I'm really getting short on space here, but we can manage. I'm going to multiply both sides by x minus 3. Minus 3. I'll rewrite that in a second. Cross those guys off. You get negative 2 equals negative 4. And that little blur right there is x minus 3. I'm going to distribute. Be careful with negative signs. So that becomes positive 12. And walk the dog all the way home. So you get negative 14 equals negative 4x. Combining the negative 2 and the 12. I'm running out of room. I'm going to come over here. So I have negative 4x equals negative 14. I just brought this equation over here and rewrote it. Divide by negative 4. Oh, and this one's reducible. Negative divided by negative is a positive. 14 divided by 4 is 7 halves. So the x-intercept is 7 halves, comma 0. And again, you can write 7 halves or you can type 7 halves, but in your mind, 7 halves is 3.5, yeah, or 3.5. If you have to use your calculator, then do it. I'd rather you do that than input the wrong thing or interpret it incorrectly. So again, summarizing, you have your domain, you have your vertical asymptote, you have your horizontal asymptote, you have your x-intercept and your y-intercept. In that sketchy little graph that I had over here a minute ago, if I would have drawn it on graph paper or perhaps using the computer graphing tool, which I'll get to maybe in part 2 of this video, looks like we're going to have to go to part 2 because I'm already almost at 50 minutes. So I might only have time for one more example today. So that's that. All right, let's do one more, and then maybe I'll have time to bring up the computer model and show you how that's done using the computer. So example 4 is going to have to be the last one for today. So come on back. There we go. So example 4, we got f of x is negative 2x minus 3 over x plus 1. Okay, so what we're going to do is we're going to answer all the same questions: domain, x-intercepts, y-intercept, x-intercept, y-intercept, vertical asymptote, horizontal asymptote, and then I'll bring up the computer software and show you how to input the final answer nicely, a lot neater than what I had before. Okay, so let's go ahead and do it. So let's go ahead and do the domain. After these first 3 examples, I hope you can just do it mentally, right? So x is not equal to negative 1. Or in interval notation, that would be negative infinity to negative 1, union negative 1 to infinity. Saves me a lot of board space. It also gives you the vertical asymptote. That's x equals negative 1. Remember, the vertical asymptote is an equation, so you have to type it as x equals -1. The horizontal asymptote. Right. Now, again, you can do this mentally. Let x get very, very large. Right? So maybe here, this is mental math here. Let x get very, very large. So let x go towards infinity. Yeah. And again, you can't really plug in the symbol infinity. So you can use, 1,000 or something. So that would be 2,000. Yeah, if you plug in 1,000 minus 3 over 1,000 plus 1. Well, that's essentially 2,000 divided by 1,000, right? In other words, you can ignore the -3 and the +1. It's a little more, it's intensified if you use a bigger number, right? You have 1,000,000. Well, clearly, if you have 2,000,000 and you take away 3, you can see that the insignificant value of the -3. And similarly here, if that was 1,000,000 and then you added 1, it's like, oh, you've got 1,000,000 and then you add 1 to it, it's still 1,000,000, right? It's 1,000,001. The whole point is that you understand that this is a tendency, right? It's not actually equaling this value. That's why I use the squiggle. Yeah. Or in calculus, we use the arrow to say it's going towards that number. But either way you slice it, this is approximately -2. Yeah. Which you can kind of see the pattern there. All right. I'm going to summarize that at some point because these problems are going to get a little bit more intense in the next section. So my horizontal asymptote is y equals -2. Y equals -2. And this was I called it mental math, but I did it on paper anyway. All right. And then the x-intercept. Set the numerator equal to 0. I know last time I did the y-intercept first, but this time I'm doing the x. Set the numerator, that's your p of x, equal to 0, and solve it. And you're going to get -3/2, which is a terminating decimal. So if you want to type it as -1.5, you can because it terminates -3/2. Or you can leave it as a fraction. Yeah. And then the y-intercept, you plug in 0 for x, and you get -2 times 0 minus 3, and 0 plus 1, which is -3/1, which is -3. So the y-intercept is 0, -3. Okay, write these numbers down and the set. Oh, this is the way I want the domain for this question. In fact, for all the questions, that's the way you'll type it. This is the way I think of it. And this is the way I type it. Unless otherwise noted. All right, so write all that stuff down, and I'll bring up the software, and I'll show you how to graph this, and we can wrap this section up. I've got, let's see. I'm trying to bring it up to the screen. Okay. I don't know if you guys can see that. The equation is slightly different. So let me just use this graphing tool to graph the one we just did. And then next time I will use a different one. So is that showing up there? I don't know if you can see that. Well, hopefully you can see the graphing window. Now, I just pulled up a random homework problem from your homework. So I'm just showing you the way the graphing tool works in this example here. Don't worry about the actual equation for it now. So you're going to click on the tool. Now, for this particular section, I removed all the other tools, so you just have the one tool for the reciprocal. So you're going to plot the vertical and horizontal asymptotes at the same time. So we have the vertical asymptote was -1 and the horizontal was -2. So we're going to go to -1 and -2 and click. And that gives you your asymptotes. And then just pick one of the intercepts, whichever one looks the easiest to graph. This will let you do halves. So you could do the x-intercept, which is -0.5. You see how I have it right there on -0.5? And then you'll notice in the other region, it does cross at -3. So both of the intercepts, the x and the y-intercept, should match. Or you could come down here to -3 and click, and then you'll notice that the other intercept is still -0.5. I usually pick the one that's an integer. Okay, and so that is what the graph would look like on your homework. If I click submit question, it'll actually mark it wrong because this problem was slightly different. The one that I'm using is -x + 8 over x - 2, which is one of your homework problems. Very similar to the one that I just did, but I just wanted to show you how the graphing tool works. So I guess that's going to have to do it for today. This is Dr. Jordan reminding you to do your homework. And until we meet again, I'll see you on the internet.